properties over here and try to write down the tools that we're going to use to show these properties over here. Okay, so it says prove that both pairs of opposite sides are. What is one way to deal with a quadrilateral? Show it, it's a parallelogram by looking at both pairs of opposite sides. What can we show? Okay, so both pairs of opposite sides are. What does slope tell me? What slope is the quality that you're looking at. It's the quantity that we're going to calculate. But they're going to tell me that the side. When I look at the slopes and I relate them, it's going to tell me the sides are what to one another? Not equal. Parallel. Okay. So over here on the left-hand side it says prove that both pairs of opposite sides are parallel. That's what we're looking for there. And then we're going to go off of what he said in regards to how do we do that? How do we determine something is parallel in the coordinate plane? We look at slopes. And slopes have to be equal. Equal slopes tell you that your lines are parallel. And you remember your slope formula, hopefully. I'm going to write it here, y2 minus y1 over x2 minus x1. Okay, that's a good idea to be able to do that. All right? That's actually going off the definition of a parallelogram, right? Definition says both pairs of opposite sides are parallel. What's the other thing or the other feature that we could look at to determine that it's a parallelogram based off of both pairs of opposite sides? Okay, so they're congruent, and you're saying then when I want to talk about congruency, that incorporates the distance formula. All right, we want those distances to be equal, right? Remember our distance formula. Distance is equal to, I'll put the square root here in a moment, but x2 minus x1. I'll put the square in there as well, plus y2 minus y1. So our distance formula looks like that thing there, okay? Hopefully at this stage, not an issue to deal with, okay? Something that we've done a lot in this course, and I'm to the point that when we deal with the distance formula, I'm not going to write this out, okay? I'm not going to walk through the explanation of how to use that and what the x2 and x1 and y1, y2, what those things mean. I think that should be known by now if you've been breathing in this class. Step 3, or option 3, is to prove that both pairs of opposite angles are, what do you know about opposite angles of a parallelogram? They have to be congruent as well, okay? Now, I'm just going to write here that this is not easy, okay? Generally speaking, if they're right angles, it's really easy. But if they're non-right angles, that is a very difficult, elongated process where we have to use sine, cosine, tangent, law of sines, law of cosines, distance formula, and then work all those things together to really use that, okay? Which will be something we focus on in chapter 7, 8, and 9. But right now, that's not an approach that we're going to use at all in proving a shape to be a parallelogram. This one, prove that diagonals. What do the diagonals have to do to one another in a parallelogram? Good. Bisect each other. I'm going to write, instead of each other, I think one another might be a better phrase because it tells me that the first diagonal bisects the second one, and the second diagonal bisects the first one. Okay? There's a couple different things you could use here. All right, but I'm going to give you the one. I'll talk about the one that is the most efficient, the quickest. Okay, which really encapsulates the second idea. That if we talk about the idea of bisectors or segment bisectors, we need midpoints, right? And midpoints develop a point that we can use the distance formula with to find four distances of the kind of the partition diagonal. Okay, so we could use this formula. That's what we're paying about. Nobody wants to use the distance formula 4 times. Okay, but what gets wrapped up, and we'll talk about this when we do this first example. The way we can geometrically in the coordinate plane show that diagonals are bisecting one another is to use midpoints. Look at midpoints of diagonals, and we want to see that they are the same point. They have the same x and y coordinates. Okay. If you remember, hopefully you do, we're going to take x1 plus x2, and we'll divide that by 2, and then we'll have a comma, and then we'll have y1 plus y2, we'll divide that by 2, and that's your formula. We write it as an ordered pair, but that's your formula for finding midpoints. Add the x's divided by 2, add your y's divided by 2. Okay. Option 5 is, if you remember one of our theorems from 6.2 and 6.3, said that you could actually focus on just one set of sides, opposite sides, and if they are both parallel and congruent, then you have enough information to show that this thing is a parallelogram. So obviously that one's going to deal with slopes and distances. Okay. Well, what's nice is you only have to worry about one pair of opposite sides. Okay. So maybe I only have to find the slope twice and then find the distance twice. Which might be something to think about as we work through, and maybe we draw a connection to what we've done in 6.1, 6.2, and 6.3 with some of these coordinate geometry questions. If you remember, if I find the slope, let's look at that bottom question there, J-O-Y-S. If I find the slope of J-O, then I have the components necessary to find the distance. Because in both formulas, in slope, we got y2 minus y1, right? In distance, we have y2 minus y1. In slope, we have x2 minus x1. In distance, we have x2 minus x1. So if I find the slope of one of these segments, it's really easy and efficient to find the distance right away. So that might actually be one of the, even though you're using two formulas, it might be one of the quicker ways to show that a shape is a parallelogram, quadrilateral parallelogram. Okay, now I'm not saying that you have to do every one of those things on these questions. Okay, my hopes are that you understand all, I'm going to say 4 of them, because we're not going to do the one with the angle, but you understand those 4 approaches, understand the components, and the approaches are dictated by the theorem. So if you don't know the theorem, you're not going to be able to use the approach. Okay, so that's very important as we move on. I'm going to use, I like this statement number 4 here. I like to show that diagonals bisect one another. If we were to write our formulas out and think about the formulas that are the easiest to deal with, midpoints is probably the easiest one to deal with. It's the only one that deals with addition. We'd rather add and subtract, right? There's no square roots there. It's a very nice formula comparison, and in comparison to the other ones. So I want you guys to come down here and just plot those 4 vertices, J, O, Y, and S. Your picture's going to be kind of ugly, muddled. I think this is a 10 by 10. Huh? Right. So there's your Y's, your Y axes, and there's your X axis, right? I believe from 0, 0, there's 10 units this way and 10 units that way. So that might help you plot S a little bit quicker. I'm going to use, just because I think it's a little bit clearer and less muddled, I'm going to use GeoGebra to kind of walk through the explanation of this stuff. something that I found that benefits me. I'm not saying it's going to work for you or be useful for you, but I think it probably will be. When I'm dealing with these pictures in the coordinate plane, the reason I graph it is just to organize my information. Okay, but I also think that it's useful to put in that in the coordinate plane that J has the order pair of 1, 1, that Y has the order pair of 3, 3. Draw that on my graph because it would really be kind of problematic to always have to go back up to the directions to say, okay, what was J? Okay, now go back to the direction. Now what was O, and that kind of thing. If it's all there in your picture, it allows you to kind of work through the problem a little bit quicker. I'm going to, just because I want to write on this thing a little bit easier, I'm going to get rid of the grid lines, but is everybody okay with that in regards to realizing that the coordinate plane is still there? And what we're going to do here is deal with trying to prove that this quadrilateral is a parallelogram. Now, it looks like a parallelogram, which is nice, but on the intercourse exam, if you get a picture, you plot the points, and your argument is it looks like a parallelogram, your points are going to be 0 out of whatever. Okay, they're not going to give you credit for that. You need to show an argument. You need to have validation of why you think that's a parallelogram. Okay, I think this is the situation where you could say, well, let's look at slopes. Okay, and you would kind of on a personal basis to see which one of these is the best for you. Maybe you time yourself on doing each of these 4 approaches. Okay, which one was quicker? Okay, or which one was I most efficient at in regards to getting the right answer the quickest? Okay, but if I looked at slopes, is it kind of easy to do slope of this thing if I've got these points written this way? Can I go y2 minus y1, so I get 7 for that slope, right? Or for that numerator. And then 2 minus 3 would be -1. Is that kind of easy to do that slope? Okay. My suggestion to you is not to just say, just write 7 over -1 arbitrarily in my picture somewhere. You're going to want to write that is the slope of SY. Okay. So organize your work a little bit better than just writing random values anywhere. Now if I do y to O, so slope YO, subtract my y's, 3 minus -6 gives me -9, right? Oh, sorry, I messed that up. And this might be beneficial for us to write this down. 3 minus -6, that turns into what? +9, right? So 3 minus -6, and then 3 minus 2 gives me 1. Okay, so that's that slope 9 over 1. Come over here, I'll do OY, so OJ. I don't know my alphabet. OJ, so 1 minus -6 gives me 7. 1 minus -6 gives me 7. 1 minus 2 gives me -1. And the nice thing there is that slope right there, is that equivalent to that slope right there? So now you know those 2 lines are parallel. Then we're going to find the slope of S to J. So slope SJ. I'm going to go 10 minus 1 gives me 9. And 2 minus 1 gives me 1. And now you see that slope of 9 is the same as the slope of 9, right? So by the definition of a parallelogram, we have shown this quadrilateral to be a parallelogram. The definition says it is a quadrilateral, that's what we have, with both pairs of opposite sides parallel. And that's what we've shown. You need to show that word to get the credit for the question. You need to be able to explain yourself and say, why did I do that work? Okay? And the explanation of why you did that work is because you know the definition says that both pairs of opposite sides need to be parallel. And slopes are the word to show that lines are parallel. Is that all right? Now, just depending on how your comfort level with that slope formula, hopefully it's a really good comfort level. But that might take you longer than you want it to. Okay, so let's see if there's a different approach. We should be able to come up with the same exact argument that this thing is a parallelogram by looking at something else. And I want to look at the midpoints of the diagonals. Okay, so I'm going to draw my diagonal in here. I'm just going to look at JY. Okay, so if I look at JY's diagonal, okay, I'm I'm interested in whether the other diagonal from S to O is going to bisect that. Does that make sense? Well, if this segment S to O is going to bisect YJ, it has to go through what of YJ? What does every bisector ever pass through for a segment? The segment's midpoint, right? So let's find the midpoint of JY. So the midpoint of JY is in X comma Y. And all we do is we add the X's of J and Y, divide by 2, and then add the Y's of J and Y and divide by 2. So that should be something that we can do pretty easily. Add the X's, 1 and 3, divide by 2, you get 2. Add your Y's, 1 and 3, divide by 2, you get 2. So the midpoint of this thing is 2 comma 2. It's that point right there, right? Okay. Now, what I want to do is see, okay, does this segment here, make it, that's ugly, make it that blue, okay? Does that segment pass through that midpoint of 2, 2? Now, it looks like it does, right? But don't ever go off of looks, because what if I had, let's see here, what if I did this? Well, I messed things up a little bit, but so I changed the parallelogram. But does that blue segment look like it goes through that midpoint? No. Okay, so you're saying it's off a little bit, right? But if I zoom out now, maybe it does look now, right? But if I zoom in enough, we see that blue segment does not go through the midpoint of this red segment now, right? Okay, and that's because I messed up. I dragged the point here and I messed up the parallelogram. So let's go back to wherever we were. There we go. All right, so that's the parallelogram that we're interested in. Okay, and I want to see, even though it looks like it, can we show the math that proves it? Okay, because that's what we're interested in. So what we're going to do is, I know that 2, 2 was on the red line, right? To prove that that blue line is going through 2, 2, we need to show that 2, 2 is on the blue line. Does that make sense? If 2, 2 is on the red line and 2, 2 is on the blue line, does that mean that they're sharing that point and both lines pass through it, right? So I'm going to find what happens here. The way we do this, I'm going to find the midpoint of SY. Or sorry, SO. Sorry. So SO are those 2 points. I'm going to find its midpoint. Okay, so I add my x's. 2 plus 2 is 4. Divided by 2 gives me 2 again, right? 10 plus negative 6 is 4. 4 divided by 2 gives me 2 again, right? Okay, so what we're saying here is, now, because they share that point 2, 2, okay, and 2, 2 is the midpoint of the red, and it was the midpoint of the blue, right? And that point 2, 2 is on the red segment, it's on the blue segment. So we're saying, because it's the midpoint of the red one, the blue, by definition, is a bisector, because it passes through a midpoint. Does that make sense? So the blue one is bisecting the red one because it passes through the red one's midpoint. And the red one is passing through the blue one's midpoint, so the red one is a bisector. So have we shown that each of those is bisecting the other one? Just by showing the midpoints. Does that make sense? So anytime that you can show the midpoints to be the same point of the diagonals, you have shown that diagonals are bisecting each other, and you have effectively shown that that thing is a parallelogram. Because at any time a quadrilateral exists in which the diagonals are bisecting one another, we have a theorem that says that that quadrilateral has to be a parallelogram. Okay? So what I want you guys to do is flip to page is it page 2? Yeah, page 2. And it starts talking about now trying to prove that a rectangle or a quadrilateral is a rectangle. Okay? And this is the way that I think you guys should do that. I'll leave these up here so you can write them down, just because we're kind of running out of time here. I would probably write, we did this in the last class, but I would probably write, prove that it is a parallelogram with, and then in this box here, write one right angle. Okay, and you're going to then make that conclusion based off slopes. Okay, what do slopes have to be if you're going to have right angles? Okay, I hope the silence is just reluctancy to talk and not ignorance. Okay, I hope we all know that slopes are opposite sine reciprocals when two lines are perpendicular. Okay, so showing that the first thing you have to do there is show it's parallelogram, though, right? So you have to do what we just did on the last example first, and then go through and talk about slopes. Okay, the second option there is to prove that diagonals are congruent. Let's write this way: congruent diagonals. And then the algebra that you go through is to use the distance formula, right? Which hopefully we have committed to memory. And the last one is actually the definition here. What is the definition of a rectangle? Four right angles. So prove that all angles are right angles, or in this case, you would be showing that they're all congruent. But that showing angles congruent in the coordinate plane is hard. Showing that they're the right angles is a little bit easier. And we can actually maybe condense our work or eliminate some of our work, because the way we're going to prove it is to show that all angles are right angles, and that would be four things, right? But if I'm able to show three right angles adds up to 270 degrees, right? Quadrilateral is supposed to have 360 in it, right? So that would be, if I have 270 already eaten up, the last angle would be 90 as well, right? So you don't need to necessarily show all four angles right angles. You can really just show three right angles. And then by default, the fourth one will work. However, in finding that three right angles exist, you're going to do the work that looks at or uses all four. And it's just going to be kind of a recognition thing to find that fourth one. All right, so if we look at this example here that talks about SNOW, I'm going to look at that thing right there, and a couple different approaches you can use. Okay, if you want to go off the definition, I think people are comfortable with the definition of a rectangle, and you need right angles, right? So if I need right angles, the only way we can do that in coordinate geometry is talk about slopes. So I need a slope of NO. Hopefully you guys realize that when we have the picture written this way, it's really easy to find slope. Take your y's, 7 and 2, subtract them. Take your x's, 4 and 9, and subtract them. And I get 5 over negative 5, right? Now I'm going to do the same thing for OW. So slope OW. Take my y's, 2 and negative 5, subtract them. Then 9 and 2, subtract them. So here, I get positive 7 over 7, right? Now, this is a situation where people think, well, they're not opposite sign reciprocals. But they are. What's 5 over negative 5? Negative 1, right? What's 7 over 7? 1, right? 1 over 1 and negative 1 over 1 are opposite sign reciprocals. I write 1 and negative 1 as fractions. Or if I go through the product property of perpendicular lines, we said the slopes multiply together give me negative 1, right? Does negative 5 over 5 times 7 over 7 give me negative 1? Yeah, it gives me essentially negative 35 over 35, right? And that reduces to negative 1. So those two lines are indeed perpendicular. So we got a right angle right there. Okay. Now, because we haven't done any work to show this thing is a parallelogram yet, all we know it's a quadrilateral, right? And there are quadrilaterals that exist that are not parallelograms that have one right angle. Okay. Some trapezoids have a right angle. Okay. So we don't know this thing to be a rectangle yet. So I would find the slope of SW. We're finding the slope now of SW would be 0 minus negative 5. So that's 5. And then Negative 3 minus 2 gives me negative 5, right? So that slope is negative 1. And now I'm going to find the slope of Sn. And then that gives me 7 minus 0 is 7. And 4 minus negative 3 is 7 as well. And that gives me 1. Does that make sense? Okay. So if I'm looking at these things, is this slope here opposite sign reciprocal with that one? So these two consecutive sides have opposite sign reciprocals. So that's a right angle, correct? Are these two, is that one and that negative one, are they opposite sign reciprocals? So that's a right angle, right? So you have enough, that's the idea. We've shown 3 right angles, so that's a rectangle, right? But the idea is that you've already done the work to really show that this one's a right angle as well, because you've already done that slope, and you've already done that slope, right? And they are opposite sign reciprocals, okay? Here's something you could have done, okay? And I'm going to let you out once I get done talking about this. But you know, let's say that this was, you found this slope here to be negative 1, and this slope here was positive 1, right? If we would have done the work to find the midpoint of that thing, add your x's, divide by 2, so it gives you, 3? And add your y's, divide by 2, gives you 1, right? So the midpoint of that red segment is 3, 1. If you find the midpoint of that segment, okay, add your x's, divide by 2, gives you 3. Add your y's, divide by 2, gives you 1, right? So when I find that midpoint right there is the midpoint for the red one, it's the midpoint for the blue one, this is a parallelogram, right? And if I go through and I find that slope and that slope, you have a parallelogram with one right angle, right? And a parallelogram with one right angle actually has how many right angles? 4. So it defaults to a rectangle, right? Okay. So there's a lot of different types of work that you can do and groupings and collections of work that you can do to prove things to be rectangles, rhombuses, and squares. The idea is, or the thought is, that you should know those 3 or 4 formulas. We've been using those all year. Now you have to concentrate on the properties that tell you which of those formulas to relate to one another so that you can make the argument. Okay? What I want you to do for homework this evening is on page 3, there's this chart with rhombuses, right? I want you to fill that in just like we did with parallelograms and rectangles. Then I want you to do the first question right here with NEWI. Then I want you to go to page 4, and I want you to do this chart. Okay? And I want you to do this first question right here. All right? Now, your neighbor might do it completely different than you do, but you both should come up with the same conclusion, right? Your neighbor might use this option here, and you might use this option. All right? That's what I want you to do for homework. Have that ready to go tomorrow, and get out of here.